Okay, so let's come back to one thing that happened yesterday, somewhere in the middle of the talk. You remember that we considered a discrete time random walk on the cube, and then we took some sort of a limiting object after time rescaling, right? We made our walk lazy with some parameter lambda going to 0, and we have seen that after a linear time rescaling, we got some particular behavior of this limiting object, right? That was the way to produce some continuous time behavior out of the rescaling of a discrete random walk. That was one thing that we did, and just to keep this on board, I copied the outcome of our computation. So if F0 denoted the starting distribution, the probability distribution of finding our point at a given vertex of the cube, that was this sort of expansion, then the probability of finding our point in our particle in the point x after a time n times t divided by lambda was going, when lambda was going to 0, to this quantity. Right? So the formula showing how our density of a particle evolves with time was a multiplier sort of formula. Right? We have a factor exponent minus 2 times t times cardinality of the index set S. Okay, so let us keep it for the record on the board. And then, let me just remind you, we considered a different sort of thing. We considered the standard Poisson process. Then we considered parity of this process. We computed the transition probabilities for the parity Poisson process. And we did some technical time rescaling by a factor of 2, so that the transition probabilities to erase this 2 from the exponent, just to make things a bit simpler. Okay. And, well, we introduce a new way of moving on the cube in continuous time. So the first one was just the limit of the discrete random walks with time rescaled. And the other thing that we defined looked as follows. When we start from vertex V, we start flipping randomly coordinates according to this process X, which is just Poisson parity process with time rescaled, on each coordinate separately. Right? That was the other thing that we considered yesterday. And well, we said that once we have such a process, this is a Markov process, it always leads to definition of some semigroup, some Markovian semigroup. We described the basic properties of such Markovian semigroups, and also we discussed, that was a complete proof actually, but I understand that it was difficult to follow all details during the lecture. But anyway, we discussed basically the idea that there is one-to-one equivalence between Markovian semigroups and Markov processes, right? At least for discrete structures. What I presented was a complete proof. So that was the place at which we finished yesterday, just understanding how to recover the transition probabilities from the semigroup, and also we know how to get the semigroup once we have the Markov process. We understand that these two things are equivalent. So now let's see what is the situation with underlying measure. So measure mu, in our case, is just a uniform measure on the cube, the normalized counting measure on the cube. But in general, it may be some measure mu on the finite finite space of states, and we can consider some more general Markov semigroup Q with density transition Qt xy. Let me remind that this is probability of moving from x to y in time t. And then we can say what this means, that mu is a stationary distribution for this Markov process. I'm pretty sure all of you have seen this, this sort of object before, and let me just remind briefly. This means that the total immigration to the point y is exactly balanced by emigration from y, right? We move from y to other points in our state space, but also we have migration from other points of the space. So the total immigration is mu x times qt xy summed over all x's in our state space, right? This is how much probability comes into the state y in time t. And of course, all that we had in the beginning in y emigrates to other points, right? And of course, part of this emigration may be just going from y to y in time t, right? But this appears on both sides of this equality. Okay. So we will say that mu is a stationary distribution or invariant measure for our semigroup or Markov process if such equation is satisfied. But what this equation means? This is exactly the same as saying that expectation of qt y 1y, which is just indicator of a single point y, is equal to expectation of 1i, right? This means that the semigroup Qt preserves expectations of when you evaluate it on indicators of single points, right? Just because this expectation, when you write it using the definition of expectation, and you recall the fact that the transition probability is defined for our semigroup exactly by this formula, that this is the value of the Qt indicator of y at point x. Once you recall this, you see that this amounts exactly to this fact. But indicators of single points span the space of all functions on our discrete probability space, right? And this equation obviously is a linear thing in terms of the function. So once we know this for all indicators of singletons, of single points, we know this for all functions, okay? So we have proved that the invariant measure has this probability that that the semigroup preserves expectations of all functions, okay? And in fact, this reads both ways. As we will see soon in few slides, if the semigroup is symmetric, which is not necessary, this is actually the case for our random walk on the discrete cube, both in discrete time and discontinuous times random walks. They are symmetric with respect to the uniform probability measure on the cube. But in general, this doesn't have to be so. But if the semigroup is symmetric, and I will explain later what this means, and it preserves the constant function 1, then it also preserves expectation. And if it's symmetric, this implication goes also the other way around. If the semigroup preserves expectation, then Qt of 1 is equal to 1. So these things are sort of formally equivalent. This is just the way of reading the fact that the semigroup preserves expectation from this equation. But only if the semigroup is symmetric. We have such a simple situation. Okay. So we remember that this is what denotes the fact that mu is a stationary distribution. Okay, so now...
Can I ask something?
Yes.
Can you perhaps say a few words where we're headed? I mean, I see the details, everything is very clear, but somehow I don't understand what are the main things that we are trying to accomplish.
We are trying
Spend a
to,
minute or two.
okay, we are trying to understand the behavior of this basic object that I want to introduce, which is the semigroup related to the continuous time random walk. I'm trying to show you this object from different perspectives. And, well, this is just Markov chain perspective, right? We have seen also this limiting approach, and in the end I want to show you that all these things converge to one object actually, right? This is just to show you different properties of that. So this of course is just sort of recollection of the things that most of you have learned at Markov chain class, right, at some point of your studies. Okay, so now a short warning. Let me just recall what I said about Markovian semigroups, that they preserve the function constant equal to 1, and that they preserve order, and they are linear, and also, well, they are semigroups in the sense that when you take composition of Qt and Qs, you should get Q indexed by T plus S, right, the semigroup property. So, all these properties do not imply that the semigroup is continuous with respect to time. And there are simple examples showing that this doesn't have to be the case. So for example, consider the following trivial semigroup. You can set Q0 of f identically equal to f. Does Q0 equal to identity? Because that was one of the conditions that we impose on semigroup. But for all positive t, you just set Qt of f equal to expectation of f, right? So it's very easy to check that this object actually satisfies all conditions that I told you about, right? For function constant equal to 1, it will send to function constant equal to 1. Whenever you take composition of Qt, Qs, you get again expectation, right? Everything is satisfied. But this is not a very satisfactory thing, right? So it satisfies all conditions, but it's not a nice object actually, and it's sort of trivial. In particular, this is not continuous with respect to time t, right? Even for a fixed function f, there is no really hope for having a continuity, unless we are on some very specific and trivial space when we have just one point, right?
This mixes instantly.
Yeah, yeah. In infinitely small time, it mixes totally, and then nothing changes, right? So we want to avoid this sort of situation. In fact, what we want to consider, we would like even to differentiate this semigroup, right? So let me just very briefly tell you what is the basic idea, how to arrive at the situation that you can differentiate the semigroup. So one of the basic assumptions that is made usually, additional assumption, is that for fixed f, the function sending t to qtf should be continuous. That's an additional assumption that usually is made. So in other terms, qt sent to qt should be strongly continuous, in other words, on zero infinity, right? So whenever you have such assumption satisfied, you can immediately produce a dense set of functions, or at least a very large set of functions, depending on what structure you have on your function space, which are all functions of the form q epsilon f. You take arbitrary function f, then you run the process for a small positive time epsilon, and then it's easy to prove that this function already has a nice property that the semigroup on this function can be differentiated. Okay, this is the general idea. Once you run the process for a very short time, whatever function you started with well, whatever means measurable L1 or L2, depending on what setting you choose in the beginning. But almost whatever you take in the beginning and you run the process for a very short time, if only you have this sort of assumption, the semigroup will smoothen the function so that for all times you will be able to differentiate your semigroup, right? I will not get into details. This is part of the large subject that is called semigroup theory, Heliosida theorem, and so on and so on and so on. This is just to tell you what is the basic situation. In our situation, when we work on the discrete cube, everything will be just for free, just because our semigroup has very simple structure and everything is finite dimensional. Okay? But even when you do things on the Gauss space, which is very simple relatively to other things that you can imagine are done in this theory, even on Gaussian space, things are not so simple anymore, just because the situation becomes infinitely dimensional, and differentiation cannot be done for all functions. Whenever you are in the infinite dimensional situation, you are obliged to really take care about what functions f you consider when you want to differentiate the semigroup. Right? This is just a technical remark. In whatever we will do later on the cube, things will be trivial. But this is a very special case, and only thanks to the fact that cube has finite number of points and therefore everything turns finite dimensional. Okay? Usually things are not so nice, not so lucky. Okay, but anyway, whenever this thing is well defined, whenever we can differentiate the semigroup, we call the derivative at zero, of course this is one-sided derivative, a generator of the semigroup Qt.
So you've got a minus.
Yes,
Probabilists don't use.
There are several comments here. Depending on the community of people who do that, you either write this minus or you don't, right? There are differences between different subsets of probabilists, people from partial differential equation, and so on. So if you want this generator in our situation to be a positive semi-definite operator, which is a nice thing, then you write it as I did. But for example, in many situations, people would rather like to avoid having minus in expression, and they don't care, then the operator will be minus something positive semi-definite, right? It's like with a Fourier transform and many other objects. That's depending on a book or a person, you will have a slightly different notation, okay? So I keep to this definition. So maybe I will write it on the blackboard for the record. So for us, generator, called also quite often infinitesimal generator of the semigroup, will be minus d over dt. The semigroup at time, of course this is the one-side limit. Okay. Here I write our particular semigroup on the cube because this is what we will be actually most interested in. But the thing can be defined for general Markov semigroup. Okay. So now let us see what happens for our particular semigroup Pt. This was the one that we defined using the parity Poisson process, right? You remember that we have these x's that jump between -1 and 1. We know their transition probabilities. So the transition probabilities, let me remind what they were. Probability that x at point t is equal to 1. That was 1 plus Okay. And the same if you have -1 here. And if we change the sign, then of course we have the complementary probability. These two things have to add up to 1. And the same if this is 1 and this is -1. Okay? So in our case, we start at time equal to 0. That was for t greater than s, equal than 0. But we will be interested in the situation when s is equal to 0. And we want to see what happens after time t. So these probabilities, and we also assume that x0 is equal to 1 almost surely. We start all these processes from 1. So you can read from these formulas that the probability that x at point t is in 1 is 1 plus e power minus t over 2, and probability that at time t x is in -1 is this number. Okay, this is just recalling how this process is behaving. That was the thing that we discussed yesterday. Okay, and this happens on each coordinate separately. So now let's try to compute pt on the Walsh function ws. Okay, you remember that we have this process that runs on n coordinates. On each coordinate separately, we flip the time according to this Poisson parity process xi. We start from vertex v, which means that at time 0 on the ith coordinate we start from vi. Okay, and now we try to compute how our semigroup pt behaves on the Walsh function ws. We have some subset of bracket n, and we want to compute this thing at some point v. Okay, so what do? We take the process, this continuous process on the cube, moving independently on each coordinate. We start it at point v. That's the point at which we want to compute our semigroup. We see where it happens to be at time t after starting from v, and then we compute the value of Walsh function at this point, and we average over all possible trajectories. Right? That was the definition. That's how we get the semigroup from the Markov process. Okay, but in our case everything is very explicit. We know what ws is. This is the Walsh function, so we have just the product over all coordinates that fall into the set S. And we know exactly what xv at point t is, because we know that on each coordinate things happen independently, right? We start from vi, and after time t, just we have vi multiplied by xit. Okay, so this is a clear equality. Now, because these are constant things, we can just take this product out. Now, here we have an expectation of the product of independent random variables, right? We run these processes x1, x2, and so on n coordinates independently. So expectation of the product is the same as product of expectations. And we know exactly how to compute this expectation, because we know the probabilities of xt being at value 1 or -1 after time t. Okay? So this thing can be explicitly computed. And it's easy to see that everything cancels out here, and what remains is exponent -t. Okay? So we checked in a very simple computation that actually the Walsh functions ws is an eigenfunction of this semigroup, and the eigenvalue is exponent minus cardinality of s times t. So now recall that we have exactly the same situation, the same multiplier, when we look at the limit behavior of the lazy walk, when we slow time, when we use this parameter lambda to make the walk lazy and then rescale linearly time. After appropriate rescaling, we get exactly the same. You see, the only difference is this factor of 2 that is here and it isn't here. And you remember that we did some rescaling of time by factor of 2, passing from m to x, right? Just to get a simpler formula. So if you just rescale time by a factor of 2, these two things completely coincide. But what does it mean? here we have some semi-group thing, and here we have some semi-group thing. And they act at the same way at Walsh's, and because Walsh's span the space of all functions, this means that these two semi-groups coincide. So the Markov chains that are hidden, Markov processes that are hidden behind these semi-groups, must act exactly the same way, because we have seen that we can read behavior of Markov process from the semi-group. Right? That was one of the things that we discussed yesterday. Okay? So now I want to turn your attention to the fact that this is a very strange thing. Let's go back to the discrete time random walk. We have the cube. We start from some vertex. And we move to the neighboring one. But if we move vertically, we know absolutely for sure that at this particular stage of move, we didn't move horizontally. These things just exclude each other. If you move up, you know that you didn't move left, right? So there is absolutely no independence in the discrete time walk between what happens on various coordinates, right? But when you make this lazy rescaling, you make your walk lazy by randomizing the time of jumps, and then you rescale appropriately the time to get a good limiting object, in some miraculous way independence appears, right? And we have seen that we have the same thing as starting from independent sign flippings on each coordinate separately, right? So let me just make a digression over that fact, because it's, I think, good to understand what happens here. How come that we start from something that has no independence between coordinates and we end up in the object that has independence? And actually I would like to agitate you to convince you that perhaps that's the most important reason why people consider semigroups, right? Because it may seem a bit strange from some point of view that that you would like to consider such an object if you can consider just a standard random walk with discrete time, right? But the reason is that it's very convenient to have independent coordinate behavior, right? And usually it's even worth paying the price of this time randomization that makes things a bit difficult to decode the real discrete time from it. But this is not a very huge price for getting things completely coordinate-wise independent, right? So I think that's the real reason hidden behind the fact that the semigroups are so useful. Just because this poissonization of time gives you independence. Okay, so now...
Sorry, what if the structure of the cube had we used? So for example, if we did this over some canicle.
I don't think anything very specific about the cube is used
so
here.
Everything would work if we did
Yeah,
over
in fact, what I want to say now will be completely not related to graphs, and you will see that the same phenomenon happens. This is the thing that is called poissonization. I guess that most of you, or many of you, have seen that, but I think it's important to remind this notion, this technique, and also to make you see that actually what we have on the cube when you run this semigroup is exactly the phenomenon of poissonization. Okay, so now forget about the cube, we are talking about a different thing. You have a biased coin. So on one side you have heads, on the other side you have tails. You toss this coin, and heads is with probability P, and tails with probability Q. So they may be quite different. So let's say 0.67, 0.33, or whatever are your two favorite probabilities. The important thing is that they should add up to 1, and they should be positive. Okay? And you toss this coin like 100 times, 1,000 times, and you count number of heads and you count number of tails. So obviously these two things are not independent. Okay? If you have two random variables, hn and tail tn, which is number of heads in n tosses and number of tails in n tosses, they are not independent. Okay, even in the first toss you see that either you have a head or tail, right? So they exclude each other. But now we can do the same thing as here. We can take some huge number n and we can say the following. Maybe let's start without huge number n. We can take some time t and we can do the same as before, namely we can start at the situation when there are no heads, no tails. We didn't start tossing, and we do the first toss after exponential with parameter 1 random time. Okay? You wait for a while and you choose the length of this time period before you make the first toss, just exponential with parameter 1. You toss the coin. Then you wait for another independent exponential 1 time. You toss for the second time, and so on, and so on, and so on, and so on. So now you can take the following: h of t and t of t. And this will be number of heads up to time t. And this will be number of tails up to time t. But now t is not an integer. This is just some non-negative number. Okay? And the miracle that happens here is that ht and tt are independent. So this things which happens here is called poissonization. Okay? I describe this thing just for heads and tails, for something that has two outcomes possible. But instead you can throw a dice and you can have 6 possible outcomes, for example. And exactly after the same rescaling of time, you will have just 6 random processes that will become independent, even though in the beginning they weren't. Okay? So now let me try to explain where this phenomenon comes from. Why this is so? Because this is very strange when you see it for the first time and you don't get much understanding of the thing. So maybe also let me explain that ht will have the distribution Poisson with parameter p times t, and tt will have the Poisson distribution with parameter q times t. Well, let me remind, p was the probability of heads and q was probability of tails. Okay? So we have in fact 2 independent Poisson random variables, and of course when you add up independent Poisson random variables you get another Poisson random variable. When you add these 2 you will get Poisson random variable with parameter pt plus qt, which is just Poisson variable with parameter t. And that's very much okay, right? That's the number of the tosses that happened until the time t. And this is exactly what you should expect when you run the Poisson process, right?
So the way you define this process is first you choose the time when you flip the next coin,
Yes.
and then you flip the next coin
Yes.
with a probability.
The times at which you toss the coin are chosen randomly, so that the distances between them on the real line are exponential with parameter 1 and independent.
And you're saying if you kind of have 2 alarm clocks,
Yes.
one for head and one for tail, with the adjusted, correct times,
Yes.
that actually has the same distribution.
I will explain it in detail in a moment, okay? But that's basically what I say. Just let me underline one thing. HT and TT don't have the same distribution. They are independent, okay? They will have the same distribution if P is equal to Q. There are different intensities of appearances of heads and tails, right? Depending on P and Q. Okay, so now let me explain where this phenomenon comes from. Because as when you write it this way, you don't see really where it comes from. So let me use the same trick that I mentioned yesterday with discretization of time. So imagine that you divide your time into small pieces, each of them length of 1 over n. And you take capital N, go to infinity very quickly. And now imagine that you have a small dwarf that does the following. At each discrete period of time, this little dwarf is doing one of the three things. With probability 1 minus 1 over n does nothing. With probability p over n produces a head result, and with probability q divided by n, tails. Okay? So what happens when you run with capital N to infinity? How long will you wait for this little dwarf to produce a heads result? So first, how long will you wait for this little dwarf to produce any result at all? To do anything?
Exponential 1.
Exponential 1, right? You will have a geometric distribution that will converge to exponential with parameter 1. Right? With probability 1 minus 1 over n, nothing happens. And with probability 1 over n, the dwarf is tossing a coin with probability p of having heads and q of having tails, right? So because you have probability 1 minus 1 over n, well, this is easy computation. You have this geometric distribution that when capital N goes to infinity, time that will be needed for the dwarf to do anything non-trivial, to toss a coin, will tend to exponential with parameter 1. Okay, and how much time it will take the dwarf to toss the coin next time? Again, exponential with parameter 1 for the same reason, and so on and so on and so on. So you see that when capital N goes to infinity, this discrete process of little dwarf tossing the coin, but at the rare times chosen only with probability 1 over n at each discrete time, this will converge, and if you look from far away, you will be not able to tell apart this process from the process that we described. Okay? Okay, but that doesn't still explain the phenomenon of poissonization. So now let's consider a different process. I will use a blue marker for that. So now we have two dwarfs, he dwarf and she dwarf, and one of them we again divide time into pieces 1 over n everywhere. And one of the dwarfs, he dwarf, is doing the following thing. With probability 1 minus 1 over n, 1 minus p over n does nothing. And with probability p over n, sorry, I wrote it in a better way. 1 minus p over n does nothing, and with probability p over n produces heads. Okay. So we have the dwarf that is only responsible for heads. And independently of this dwarf, on the second production line, we have a she dwarf who is only responsible for tails. With probability 1 minus q over n does nothing at each of these time periods. And with probability q over n produces tails. Okay? And these two little dwarfs do not know about each other, they work independently. Okay? So what do you observe when you look at their aggregated production from far away? What happens in period of time 1 over n? With probability 1 minus p over n, 1 minus q over n, nothing happens. But this probability is quite similar to this probability, because when you multiply things and you remind yourself that p plus q is equal to 1, this is just 1 minus 1 over n plus some negligible summand of pq over n square. Okay? So with such probability nothing happens. With probability 1 minus p over n times qn, we'll have the tails produced. With probability 1 minus q over n times pn, we'll have heads. And with a very small probability, pq over n square, we'll have both tails and heads. Well, we don't like this last thing happening, right? Because this shouldn't look like that. Heads and tails shouldn't be produced at the same point. But when you look from far away, can we really tell apart this production process by two little dwarfs with such probabilities and this production process with one dwarf? We cannot. What are the differences between what happens here and here? When you look closely at these probabilities, you see that the differences are of the order constant divided by n square. But at the time period t, you have only t times n such things, okay? So because with probability 1 minus constant n square nothing differs between this and this process, then with probability of this form you will see no difference, okay? But here in exponent you have n, and here you have n square, so distance to 1 when n goes to infinity, okay? So when you have finer and finer discretization of this process, we will stop seeing differences between these two situations happening, okay? But when you look at this second process, it's clear that the number of heads produced and number of tails produced will be independent, because these two little dwarfs run independently. Okay? So that's the explanation that I wanted to give you, right? Thanks to the smart change of time, you are able to separate, to make independent things that happen with heads and with tails. Okay? So the main point that I wanted to convey to you was that exactly the same thing happens on our discrete cube. Instead of tossing the coin, you have the movement on the discrete cube, and at each point you need to choose one of the n neighbors. Okay? But actually the thing that happens on the cube, the fact that these two objects, the limiting object that we got from our lazy walk, and the thing that we got from this parity-Poisson process, they match each other, and this object in fact has independent coordinates, thanks to the fact that the poissonization works. Okay? So that was the digression. I just wanted to explain to you that this is a more general phenomenon. I think it's nice to know that such things are used, because I think this is also used in many other situations. Okay, so let's come back to our semigroup. So once we know how our semigroup acts on the cube, maybe I will write it down for the record. We know that our semigroup PT sends Walsh S to S substance. This is probably the most important formula that we need to remember about our semigroup. We know that. We are able, therefore, to compute effectively the generator L. Right? We can easily differentiate this, and from this we deduce that the generator is a very simple multiplier. Namely, when you apply the generator to the Walsh function, what you get is the Walsh function multiplied by just cardinality of the indexing set S. Okay? This is a very simple formula. And this sort of explains why we cared to make this rescaling by a factor of 2 at some point, just to have these formulas simpler, because they are used once and over again. So it's not very convenient to have this number 2 appearing in this formula all the time. The same things happens in physics when you consider heat semigroup. There is some factor of 2 that some physicists use, some don't, and there is also some freedom of the scaling that you choose to your liking. Maybe I should also tell you one more thing. Why this factor of 2 appears at all? Why there is this discrepancy? And you can choose a factor or 2 or not, and both things are sort of natural. The reason is that there is some discrepancy between time and space when we jump on our -1 cube. So in one, when you consider just usual discrete time random walk on the discrete cube, in 1 unit of time you actually move from -1 to 1. So in the spatial terms you move by a distance of 2. That's exactly the 2 that appears in this time rescaling, right? When you try to treat this cube, this discrete cube, as a subset of Rn, when you try to look at things geometrically, and this is what happens quite often, that's exactly where this factor of 2 appears. That's the reason. Okay? So, I will not mention it anymore. That was just to give you the idea where the things come from. Okay. So now we know what our semigroup looks like and what our generator looks like. Let me also mention that in a lot of literature, you will not see the semigroup PT or TT, there are many notations, but you will rather see something that is also a multiplier, but you will not have this exponential thing, but you will have just some eta in power cardinality of S instead. So easily you can see that this notation and our notation actually are the same up to some rescaling. Right? So why people would use this notation in combinatory or in computer science? This is probably more common notation. Well, just because it's simpler. You just need much less symbols to write it down. Another advantage is that actually this thing makes sense also if you take eta some complex number, for example. And you can consider this object as a semigroup that doesn't have any good interpretation in terms of positive real time. Okay? This again will be a mathematical object that you can work with, and sometimes it has very important applications. But it cannot be written this way in general. Okay? And in fact, in functional analysis, there was a lot of progress made just by considering this sort of expressions with complex eta instead of real value to 1. Okay? But for our application, it's enough to have it this way. And also, if you turn to this notation, you are missing something. You are losing this intuition that is coming from the fact that t here is the time and you have the Markov process structure and so on. So somehow there is some price that you pay for choosing this more convenient notation. You lose the intuition of the time that is behind that, and some things are not so easily described in this notation. Okay. So that's a common warning. Okay. So now that's just the thing that I did without writing it down. We can differentiate our semigroup. So as we see, we have the commutation between generator of the semigroup and the semigroup itself. When we compute derivative, not necessarily at t equal to 0, but in general, non-negative t, the derivative will be either this or this, and it's easy to see that these two operators, L and PT, just commute. This is by definition. This is using linearity of L and using the fact that we know how it acts on the Walsh functions. Now, this is some more general remark. we know that for Markovian semigroup, not necessarily for our particular semigroup, we know that Qt of constant function equal to 1 is always constant function equal to 1. That was one of the axioms of the Markovian semigroup. But this means that we know automatically that generator over on the constant function equal to 1 is equal to 0. Right? It's not only in our particular setting, but this is an easy consequence of this fact for any Markov semigroup. So for any Markov semigroup, the infinitesimal generator will disappear on the function constant equal to 1. Now, of course, you can ask the very natural question, what is the relation between the semigroup and the generator? Can you recover one from another? We know by definition how to get generator from the semigroup. Can you go the other way? Can you decipher, can you regain your semigroup from the operator L, which is generator of this group? So actually the answer is yes, and in our case, on the discrete cube, the formula is very natural. You just write Pt as exponent of minus TL. And what you mean by that? Well, you mean just an infinite series, and this series is very well defined. We are on a finite dimensional space. So L as an operator, whatever norm you choose on this function space, the most convenient norm is just Hilbert norm that we discussed yesterday, but whatever norm you choose on this function space, which is finite dimensional, L will be a bounded operator. So the norm of L in power k will be bounded by the norm of L itself in power k, so this will be convergent in norm. Right? So there is absolutely no problem with defining such a series and evaluating on any function that we want to use. Okay, and here we check this on Walsh functions. What it?
The top one, top formula. On the right hand side, the tip to the k is missing.
Thank you very much. So it should be negative t. It should be negative t in power k. Here it is, and here it isn't. It should be negative t in power k. Thank you very much. Of course, it's a typo. That should be negative t in power k. Okay, so here it already appears. And now on Walsh functions we can easily check that actually that's the case. And since both this operator defined this way and our semigroup Pt are linear, if you verify the equality on Walsh functions, by linearity you have it on the whole space of functions, right? So we proved that actually you can recover the semigroup Pt from the generator in this way. But, well, usually life isn't that nice. Even on Gauss space, the situation is no longer that good. If you are in the infinite dimensional setting, it's unlikely that your generator L is defined on all functions to start with. Right? Semigroup is defined on all functions, meaning all integrable functions, or all square integrable functions, depending on what setting you work with. But the generator L usually isn't defined on all functions. So that's the first problem one has to deal with. And the other problem is that this series doesn't make any sense usually. Even if some function falls into the domain of operator L, it's not clear whether it falls into the domain of operator L in power 2 or 3 or whatever, right? So we need a function that is that you can use operator L2 multiple times. And even then, if you do things on such functions, you still don't need to have any convergence of this series, right? So such approach is completely hopeless in general case. And usually what is meant, people would still use the notation exponent minus TL, but what is meant by this is either a solution of an operator differential equation. You just set the boundary condition Q0 equal to identity and solve the equation, and of course you need to prove that there is a solution and that it's unique, and then you call this solution exponent minus TL. So this is one way to look at that. Or you can use some other more refined machinery. So for example, if L is a self-adjoint operator, if you work in L2 and you know by some chance that L has some good properties, that this is a symmetric operator and moreover it's essentially self-adjoint, then you can use the spectral calculus. Then there are theorems saying that on the spectrum of the operator, you can take any nice enough function and you can evaluate this function on the operator itself, right? And that's the case that we have here, right? We have self-adjoint non-positive semi-definite operator. We can evaluate exponent function on it.
So for L to be defined in general, to take powers of L, you will require the spectrum to like decay smoothly, something like.
I'm not a specialist in the spectral theory. I think it depends very much on what setting you are working with. I cannot answer this question in general. I don't think it has any nice answer, actually. So that was just a warning that things that work very nicely here, and we may use them without trouble, are not easily lifted to the general semigroup setting. Okay, so the cube case is quite particular, quite special here. Okay, now there is also some more direct way of defining the operator L, this generator. I will write it down for the record. So L is n over 2 identity minus k. When you remember, k was this operator defined for the discrete random walk. Okay, so on function f, LF at point x will be 1/2 sum over all y, such that y is a neighbor of x, is in distance exactly 1 from x, fx minus fy. Okay, that's another equivalent formula for the operator L. So why is it equivalent? It's equivalent because it's enough to verify this on the Walsh functions, right? Such a definition, such a sum, is a linear form of the function f. It's linear with respect to f. And operator L that we define obviously also is linear. So if we verify that these two formulas give the same answer for Walsh functions, since Walsh functions span all functions, we'll have just the fact that this is an equivalent expression for the generator on the discrete cube. And that's actually the case. When you apply this thing to the Walsh functions, what you get is this expression. Let me just remind you that you have seen this yesterday, right? We have computed the spectral properties of the operator k related to the discrete time random walk. Right? When you add up Walsh functions over all neighbors of x, what you get is n minus cardinality of s, the same value as in point x, and there are s neighbors, cardinality of s neighbors, at which coordinate will change, and that will be the coordinate falling into the set s, so that the change of the function, the sign of the function will change. Okay, so we will have n minus cardinality of s points at which value of ws at point y will be the same as at the point x, and cardinality of s points where it will be different. Okay, so that's the outcome. So when you plug it into this formula for the Walsh function, things will cancel out, and you will see that you exactly get the multiplier with cardinality of s as a factor. Okay, so that's exactly our formula for the generator L that we got otherwise from our continuous time semigroup. Okay. Now, I told you before several times that on the discrete cube, our semigroup is symmetric. What do I mean by that? Well, I mean by that the usual symmetry that you learn when you learn functional analysis. When you have some scalar product, then operator is symmetric with respect to the scalar product if f operator g is the same as operator fg, right? So now it's very easy to verify that pt is in this sense a symmetric operator when you take the standard scalar product, right? This is the standard scalar product with respect to the uniform measure on the cube, normalized counting measure on the cube. Okay, so let's see how it works. We write down expansion of f and of g. We call coefficients standing of in the function f as AS and in function G as BS. And all the computation is very direct. We know exactly what PT of G looks like, because this is a multiplier. Okay? And we know exactly what will cancel out. We know that whenever S appearing here is different from T appearing in this expansion, right? We take expansion of G and index it with a set T, just to have a double sum. And we use bilinearity of the scalar product. But we know that these things will disappear whenever S is different from T, right? Just because Walsh functions form the orthonormal system. So all summands will disappear except the summands where capital S is equal to capital T. And then you see that exactly in the same way you prove that this is equal to this. Right? There is full symmetry in this formula between F and G. Okay? So we have proved that PT is a symmetric operator, and obviously generator L, for the same reason, is also a symmetric operator. Okay? So our semigroup is symmetric, and the generator L, in our case, is also symmetric in the same sense. Okay, now a quick warning. If we are talking about general Markov semigroups, when we say that the Markov semigroup is symmetric, we don't mean that the probability of moving from x to y in time t is equal to the probability of moving from y to x in time t. Right? That would be quite automatic if you are somehow used to using transition matrices, right? And you know what it means that the matrix is symmetric, right? That would be natural thing to do. But it's not so. So actually, let's say what it looks like on the finite probability space. The symmetry means that we should be able to change the order of computing expectation, right? The scalar product of indicator x and qt indicator y should be the same as indicator y, qt indicator x, right? If you want the semigroup to be a symmetric operator, we should be able to compute these things in two ways and get the same result, right? Symmetry of the operator qt demands that we have equality here. But if you compute this expectation, well, you just evaluate this function at point x, and you multiply it by probability assigned to point x, and here you have a similar expression. You easily see, recalling that the transition probability you read from this expression for our semigroup, you see that actually the formula for the symmetry looks like that. So somehow on the discrete cube, we actually will have this equation satisfied, but only thanks to the fact that all probabilities of atoms, all vertices of the cube, have the same probability, 1 over 2n. Okay? So in our particular case, actually we will have this formula satisfied, but only thanks to the artificial somehow fact that on the cube all vertices have the same probability. And one should remember that otherwise the symmetry that is meant when we speak about the symmetry of Markov semigroup is the symmetry of operator with respect to the L2 structure. Okay, so now those of you who are not very familiar with Markov chain may ask, okay, so I have some transition matrix Qt, and then I read a new matrix from it by, well, using this formula. You take Qtyx, multiply by mu y, divide by mu x, and you ask this new matrix that you, new transition rule that you obtain. What it means? What is it responsible in the world of Markov chains for? And the answer is that this is responsible for the time reversal. When you have a stationary Markov chain, stationary meaning that when you move after some time, it still behaves the same way, more or less. I don't want to get into details because we don't have time for that. When you have such a stationary Markov chain, you can reverse time. You can let time flow in the opposite direction. So there is interesting thing about Markov chains. Always, whenever you have a Markov chain and you reverse the time, you get another Markov chain. the Markov property is preserved under the time reversal. But it doesn't mean that when you started from a homogeneous Markov chain, homogeneous means that the transition from t to t plus 1, the transition matrix looks the same as transition from t plus 1 to t plus 2 and so on. Okay? What happens between time t and time s should depend only on the difference between s and t, more or less. That's the time homogeneity of the Markov chain. The thing is that when you take the time homogeneous Markov chain, x1, x2, x0, say, and you reverse the time, so you start with x5 and run down, you will get the Markov chain, but it doesn't have to be time homogeneous anymore. And it's very easy to understand why. Let's take as an example of such a Markov chain with transition matrix that doesn't depend on time. Let's take the thing that happens on the discrete cube when you start from some fixed vertex. So at point 0, you will be exactly at this vertex. This will be a constant random variable. At time 1, you will be in one of the neighboring vertices with probability 1 over n, and so on and so on and so on. So what happens when you reverse the time? You get a Markov chain that is in a miraculous way with probability 1 ending up at a single vertex, right? So it's quite clear that it cannot have the same transition matrix at every stage, because then there is no way it would mix, and then miraculously collapse everything to a single point, right? It's quite clear that on the last step, you just put everything to this single point, right? So this is easy to see that when you reverse time in the Markov chain, you get again the Markov chain, but no need for this time reverse Markov chain to be time homogeneous anymore. But if you put a stronger assumption, not only that this is time homogeneous, but also that it is stationary. So there is some underlying measure mu, and this measure is invariant in the sense that we described before. Then, if you reverse the time, you will get again time homogeneous stationary Markov chain with the same stationary measure, but usually with a different transition matrix. And what will be this new transition matrix? Exactly what we get from this symmetry condition. Okay? So somehow, for those of you who are not very familiar with the Markov processes, the fact that is encoded in the statement that the Markov semigroup is symmetric, that's the same as to say that the stationary Markov process that is run by this semigroup is time reversible. If you reverse time, you don't see a change. You don't see inhomogeneity in time. And if it's symmetric semigroup, you don't see a change. The transition matrix will be exactly the same as before. Okay? And then such a Markov chain is called time reversible. Okay, so this is just an explanation. Why do I say that? Just because this is what exactly happens on the cube. When you consider the cube with uniform measure, and you consider our semigroup running on it, our time, continuous time random walk on it, then if you reverse time, you will not see any change. Okay? That's a direct consequence of the fact that our semigroup is indeed symmetric. Okay. Now, let us also note, that was the thing that I promised to you, that when we have a symmetric semigroup, then it will preserve expectation. And this is just one line proof. If the semigroup is symmetric, we can write expectation of PTF as expectation of PTF multiplied just by constant function equal to 1, and then we can move PT from F to constant function equal to 1 using symmetry. But we know that PT of constant 1 is constant 1. This is Markovian semigroup. It preserves constant function equal to 1. So we have proved in one line that for symmetric semigroup, also expectation is always preserved. Okay? And the same holds not only on the cube, but for any symmetric. Okay. So now let's pass to the next notion, that is called contractivity. So whenever we have some fixed number p greater or equal than 1, our semigroup will contract functions in LP norm. So whenever you take a function on the discrete cube and you apply semigroup to it, it will not increase the p norm for every p greater or equal than 1. This can be viewed in many ways. One of the ways is to describe this semigroup as averaging of f in neighboring vertices under the random walk, and then say that this is just a Jensen's inequality. And this is absolutely valid way of proving this statement. This is nothing else than the Jensen's inequality once you write this in terms of the Markov, continuous time Markov walk. Okay? But let us see another way to prove this statement. So I will prove it in a more general setting. This inequality is just a special case of this inequality when we consider the power function, absolute value of t in power p. So we will prove this statement. And how do we prove it? When we have such a convex function on real line, it can be always described as a supremum of supporting affine functions. Okay? This is a useful way of proving such statements. Now, for every single index alpha, we have the pointwise inequality, therefore. Phi evaluated at point f will be pointwise not less than constant a alpha times f plus b alpha. But now, this is just inequality between two functions on the cube. And we know that our semigroup is order preserving. So we know that between pt of phi of f and this function will have the same inequality. But we know that pt is linear, and pt on a constant function returns the same constant function. So we know how to compute pt on this affine image of the function f. This is just, we can take alpha, a alpha out of this bracket, and pt on b alpha is just b alpha. Okay? But what this means? We have proved this inequality, right? We have proved this for one particular alpha, but because we know that this inequality holds for all alphas, we have actually proved that pt of phi of f is greater or equal than supremum over all alphas of these things. But this is just supremum over this family of affine functions of pt of f, so that's just our phi, right? Let me remind that we started with writing phi as a supremum of these affine functions. Okay? So pointwise we have this inequality, and because pt preserves expectations, because our semigroup is symmetric, we know that expectation of phi of f is the same as expectation of pt of phi of f. We know that this function is minorated by this function, and that's the end of our proof. We have proved contractivity in terms of function phi of our semigroup. Therefore, in many situations, we will hear about the semigroup pt as a semigroup of contractions. So when you look at these operators, not as operators on Hilbert space, that was the way we looked at them so far, but if you consider them as functions on LP, then you will see that they are just operators with norm not exceeding 1 from LP to LP. Okay? And actually, you know that this norm is equal to 1, because if you apply pt to the constant function equal to 1, it will just return the constant function equal to 1, right? So actually here we have equality. Okay, and for p equal to infinity, when you want to look at this thing at the supremum norm, either you can use this reasoning and just pass with p to infinity, or you can use just the fact that pt preserves order. You put your function f between minus m and m when m is just supremum norm of f, and then trivially you get just from order preserving the inequality, the same inequality for ptf, right? If the function you begin with is between minus m and m, then its image always will also be between minus m and m because of order preserving. Okay, and the same reasoning works for every symmetric Markov semigroup. There is nothing specific to the semigroup on cube at this point. Okay, So next object that we'll need, and I will write down for the record, is so-called energy functional. So this is a bilinear form. You have two functions, fg on the cube, from our Hilbert space, and you define the energy functional just as a scalar product of f and Lg. Okay, but we know already that the generator L is symmetric, therefore we know that this form is a symmetric bilinear form. Okay? Now, this form is positive semi-definite. So here we have a not so simple proof using the semigroup property and contractivity in L2, but you can easily see that this form is symmetric, is positive semi-definite just from the formula on the operator L. We know exactly what EFF looks like, right? This is expectation FLF, and if f is a function of the form ASVS, then we know what this looks like. This is the scalar product of some ASWS with the scalar product absolute value of ASWS. So because WS form orthonormal system, all terms will be killed except those that have indices matching. So what you come out with is just the sum of cardinality of SAS squared. So this is clearly non-negative. Okay, and that's the end of the proof that L is a positive definite, positive semi-definite form. It's not strictly positive just because of the constant function L returns 0, right? So this form isn't strictly positive definite, but it's positive semi-definite. This is a trivial proof. Here there is another proof if you want to go into notes later on. You can see that this also has some nice features, and in particular this works for any semi-group. This proof also can be used for any semi-group, but then you need to interpret things. This is sort of a continuous version of this statement. This statement is recovered just by differentiating something from this statement. Okay. So now there is also a simpler formula because we know that LF of x can be written in a very explicit form. I preserve it for record here. You just sum over all neighbors differences between value at point x and in the neighboring vertex, and therefore you can plug it into the definition of the energy functional. So what you end up with after some algebra is the following expression. Okay, so that's another proof that this is a positive semi-definite, just because if f is equal to g, you will have a clearly non-negative expression. Okay, so let me write also down for the record. You sum over all points x, y in Cn in the discrete cube such that they are neighbors. This is a very useful formula for the energy function. So in particular, when you take f equal to g, when you just try to see how what sort of the Euclidean structure this energy functional produces as a positive semi-definite bilinear form and symmetric, you come out with the following expression, right? This 2 powers of 2 can be put inside, and what it is? This is just a scalar product. This is just a discrete gradient. Right, you go from x to the neighboring vertex of y, which is in distance, geometric distance of 2, and you look at the difference of functions here and there, you divide by geometric distance between the x and y. And this tells you how fast the function f changes in this direction. Right? And you add up over n directions that you have available in the cube. Right? Each vertex has n neighbors. So this is the expression that is called the discrete gradient.
It's also what some other people call the sum of the influences.
Yes, and that's also the thing that many people call sum of the influences, and I hope I will come back to this notion tomorrow at some point. Okay. So, well, yeah, up to some renormalization. That's the thing. Okay, so now just to let you understand what this is related to. This is the general setting of the Markov semigroups. Whenever you have a Markov semigroup, you can look for its generator. Whenever you have a generator, you can define a Dirichlet form, which is a bilinear form constructed in a similar way. Then you can ask, can you reverse these things? So there is a relation between process, semigroup, generator, and Dirichlet form. And there is a whole complicated theory saying under what conditions you can inverse this implication and, for example, recover the process from its Dirichlet form. Right? This is non-trivial in general setting, just because you need to be very careful about the domains of the operators. Nothing is bounded. The generator is not a bounded operator. It's not defined on all functions. The Dirichlet form is not defined on all functions, but only on some dense subspace. And dense subspace only if you are lucky enough, right? This is why you define things as Dirichlet form. This, in fact, encodes some technical assumptions about this bilinear form that it must satisfy, so that you call it Dirichlet form, and so on, and so on, and so on. And that's not trivial. So let me say, for example, that you can recover generator from Dirichlet form under some assumptions. This is so-called Friedrich scheme, but it's not unique. There may be two different generators giving the same Dirichlet form. That's related to the problem that two different self-adjoint operators can actually produce the same Dirichlet form. There are many technical difficulties. Uniqueness sometimes is broken. Sometimes you completely cannot decipher things. And in general, this is very difficult. On the cube, this is very simple. But this is just to give a hint that this is a special case of some much more developed theory. Okay, so we have a few minutes, so maybe let me quickly explain the following phenomenon. That the energy functional behaves nicely under Lipschitz maps. So imagine that you have some function psi from R to R which doesn't blow distances between points too much. We have the Lipschitz condition. We have some fixed positive constant C such that for any A and B we have this inequality. So how does it influence the value of the energy functional? Instead of computing this on function f, I used the notation, it was on the previous slide, I used the notation epsilon bracket of f is just the norm evaluated on function f in both places. So when we apply this operator to psi of f instead of f, you can very easily see that the thing will be bounded by the energy of f itself with the term c square at most. Okay? And this follows immediately from this formula, right? When you can write down this energy functional in this way, you just dominate absolute values of this term using the Lipschitz property, and you end up with this trivial estimate. In particular, and that will be the case that we will use later, when you compute the energy of absolute value of f, it's never greater than energy of f itself. Okay, and that's the important thing to remember, that we have proved this fact. This will be useful later. Actually, semigroups that have this property, that Dirichlet form produced by these semigroups have this property, are very natural and important class of semigroups. For example, in France, in Toulouse especially, there are a lot of people studying this sort of semigroups. This is a natural condition for semigroups to be satisfied. And you can rephrase this sort of inequalities in terms of Markovianity, and actually, under some very mild technical assumption, this is equivalent to the fact that semigroup is Markovian, under some symmetry assumptions. Okay, and you can later elaborate this expression and write down this inequality in terms of so-called gamma 2 functional. But I don't want to get into details. This is some more involved semigroup theory. Okay, now there is something more general. So I showed you the thing on the discrete cube, just because we have a very simple formula for energy on the discrete cube. The same holds for more general semigroup, and I skip this proof. It's in the notes. If you are interested, you can get to this proof. It's a bit more complicated, and actually it also may be rewritten in a form that is similar to this one. There will be just some factors coming from the transition matrix here. But the thing will be a little bit more complicated. But this is a semigroup proof of the same thing, using a different approach. Okay, so now why do I speak about energy functional and energy stability and so on? So let's go back here. That refers to this discrete gradient. So this thing is very similar to kinetic energy thing that appears in physics, right? When you have some system of moving particles. The thing that you compute to have kinetic energy, you just compute energies, kinetic energies related to each dimension separately, and you add up these things, right? This is a very natural thing in physics. So that explains why people agree to call this sort of expressions energy functionals, right? The original thing was from 19th century physics, and later people realized that actually this is a good way of measuring the energy of the function on the discrete cube and on other structures, right? This is explained by the fact that we know that this is a symmetric and positive semi-definite norm. So it introduces some new Hilbert structure, different from the underlying Hilbert structure, and this can be viewed in terms of energy, right? And in many applications, this is actually a very useful way of measuring the energy of the function. So that's the explanation of the name. Okay, so Poincare inequality, I think, is better to leave for tomorrow, and I think that's the natural place to stop. So thank you.
All right, lunch. All right, coffee at 2 o'clock.